So the last time we were looking at how to test soft solids in simple tension. So really, it was really bringing everything together, everything we learned in the course, bringing it together and into the lab, right? Collecting data in tension, pulling on a soft solid, say a piece of rubber or soft tissue or whatever, collecting the data, the force or the stress versus the stretch, and then knowing that since the material is incompressible and isotropic and so on and so forth, there would be a relationship between the stress and the stretch, and using the data to fit the curve to the prediction. And the prediction depends on W. You don't know W, you don't know the strain energy for that piece, for that sample. So you have to guess it by looking at the data. So it takes a lot of mathematics to get there and a lot of mechanics, but in the end, it's just a simple curve fitting exercise. And it's not that difficult. If the line is straight, you have to adjust the slope and the ordinate, but if it's I don't know, if it looks like it's growing exponentially, then I say, oh, let's try an exponential like the full material. If you see that it goes up, and then it starts to siphon, then you say, let's try the gent material, or maybe you just try a new W. People come up with new candidates for strain energy all the time. So the tensile test, that's like the gold standard. That's the most common type of testing that's implemented in the lab. You could do it at home with just weights and ruler, or you could be part of a lab that has a tensile machine. But it's just one type of test. It gives you some indications, but not everything. Today we're going to do simple shear testing. We're going to see how to how to create that deformation and how to collect the data and relate it to a given W. So don't hesitate to stop me if you have questions. Simple shear, we've seen that a lot in the chapter on deformations, and so I will rely a lot on what we've seen earlier, but this is how the deformation is described. This is how to relate the reference coordinates to the current coordinates. And okay, I guess I should do the drawing, but typically you start from a cuboid. So here I made it in the shape of a cube. Really, it should be a thin a rectangle. By the end of the lecture, we'll know how or why. And what you do is, so that's your sample, and then to the sample, you glue two plates, right, top and bottom. So here it's glued, and two rigid plates. Glued, rigid plates. Yeah, you don't take elastic plates because then that would make everything messy or complicated. Yeah, so typically you take plates made of metal, and then you apply for, well, the bottom one is typically one is fixed and the other one moves parallel to the other one to create a deformation like this. Where the cuboid is sheared. All right, so here, if you have h for the height, then that's going to be conserved, right? The new height is going to be h, 1 times h. Make that smaller. And what else is there? There's the angle. Okay, I won't go into all the details because we've seen that before. That angle phi. Tan of phi is k, the amount of shear. All right, that's called the amount of shear. And then if you have, I'll do it this way. Oh, probably put it that way. If you have this coordinate system in the reference configuration, now you have this coordinate system in the current configuration. And so on and so forth. Okay, so if that's the deformation, it's easy to compute the deformation gradient, and we've done that earlier. It has constant coefficients. The amount of shear k is a constant. And then you can compute the inverse. You will find, and it makes sense, that it's the same, but with k turning to minus k. All right, the inverse of shearing this way is shearing by the same amount, but the other way. And then once you have this, you can compute B, which is FFT, and it's going to be 1 plus k squared, k. And you can compute B minus 1, can be the inverse of this, so it's going to be f minus d, f minus 1. All right, if I do b minus 1, I get the identity. And then you will find out it's of this form, 0, 0, 1. And you notice that I1, trace of B, trace of C is 3 plus k squared. I2, I think we've done it earlier. Yeah, it's also 3 plus k squared. And I3 is the determinant of f squared, which is 1. So I3 is 1. It's isochoric. Simple shear is isochoric. There's no change in volume. So simple shear is compatible with incompressibility. All right, we can see, so R1 equals I2, and they're both functions of k squared. So it means that W, which if you remember is a function of R1 and I2 for incompressible solids, is a function of k squared. So it's an even function of k. And then I can go ahead and compute compute the stress, right? Cauchy stress for an incompressible material in general as this form plus 2W1, so that means dW di1 P minus 2W2 P minus 1. You could have the representation with B squared if you prefer. I just went for B minus 1. It doesn't matter, it will give you the same conclusions. So I can go ahead and compute and write down the components of sigma. Sigma 1, is going to be P times the 1, component of the identity, and that's 1, plus 2W1, and the 1, component of B, that's 1 plus K squared. Okay, I'm going to write the other way around, 1 plus K squared W1, minus 2W2, and the 1, component of B minus 1, which is 1. Okay, sigma 1, 2 can be minus P times the 1, component of I, the identity, but that's 0, plus 2W1, 1, component of B, which is K, minus 2W2, the 1, component of B minus 1, which is minus K. So it's also, okay, I'm just going to write it like this. 2W1 plus W2, okay. Then I have sigma 1, 3. Sigma 1, 3, I can just look and see it's going to be 0. Right? I'm going to have 0 from here, and then 0 from here, and then the 0 from the identity, which is a diagonal matrix, so has nothing on the off-diagonal terms. And similarly, in fact, for sigma 2, 3, it's going to be 0, 0, and 0. Okay, so I just write this. Then sigma 2, 2 is going to be minus P times the 2, component of the identity, which is 1, plus 2W1, the 2, component of B, which is 1, minus 2W2, I'm going to write the other way, times the 2, component of B, which is 1 plus K squared. And finally, sigma 3, 3 is going to be minus P plus 2W1 minus 2W2, because the component, the 3 components of I, B, and B minus 1 is 1. Okay, that was easy. And that's in all generality. And it's going to give us a lot of information just writing this for any W, any material, any incompressible isotopic material is going to have a Cauchy stress with those components.